the question gives us a z-value or a nominal value and it asks us for an area probability, then what we're going to use is a dot dist equation. So that's directionally the way that's going to go. If we're given a z-value or we're given a mean and a standard deviation and a value that we're comparing, and we want to find the probabilistic area, we want to find what its rank would be among the full population, or what the area to the left is given that value, we use dist. If we're given a probabilistic area and we want to find a z-value or nominal value that pertain to that probabilistic area, then we're going to use our dot inverse equations. So far, out of all we've learned, this is kind of the most important stuff. So the other stuff is just putting pivot tables together and kind of formatting. But remember, either if we're dealing in standard normalized, so norm.s.dist, or is dealing in just regular normal distributions. If we have this information, we're going to use these equations, and if we don't have this information, we're going to use, if we're only given a probabilistic area, we're going to use the dot inverse. So,
Mike, for the is, I know it means sample.
no, it means standard.
Standard.
So S in this in these equations is standardized. So we have a standard normal distribution and we have just a normal distribution. The difference is a standard normal distribution. So the norm S, and we have a standardized normal distribution. Then our mean is equal to 0, and our standard deviation, I'm not going to draw the little thing for that, is equal to 1. So that means we've standardized our population, and the way we standardize our population is we take each value, we subtract the mean, and then we divide it by the standard deviation of that population, and that gives us a population where our mean is equal to 0 and our standard deviation is equal to 1. And so if we're given that, we're given a z-value. If it says z, it gives us a z. Or it says something is standardized normal distribution, then we're going to use norm.s. But if we're just dealing in just normal distribution, and they give us our values in dollars or pounds or metric tons or something like that, then we just use norm.dist and not norm.s.dist. And the big difference is, when we're using norm.s.dist, we don't have to report what our mean or what our standard deviation is, because it's already assumed that our mean is 0 and our standard deviation is 1 for the entire population. When we're using norm.dist, we have to report what our mean and what our standard deviation for the population is.
Say that again one more time. I missed the first
So
portion.
when we use norm.s.dist, we don't have to report what our standard deviation and our mean is, because it's already assumed that it's 0 and 1.
Okay.
But when we use norm.dist, we have to input into the equation both the mean and the standard deviation. So, questions on this?
The dollar value and the pounds, is that for both? For the normal?
No, this is just for norm dist. If you're given norm.s.dist, you're going to be given in z values. So it's going to be, they're going to be smaller numbers, probably between -3 and +3, that range. You're welcome. Okay, so let's look at chapter 7 for a little bit.
And how about on the other side, when you have the normal, the inverse? Would you mind to elaborate a little?
It's just whether they want you to report your answer in z value or they want you to report your answer in units. So if they want you to report your answer in units, then you say, I want to know a point on the x-axis where 70% of my observations come before that. So I'd put in 0.7, but then I need to know what my mean is, and then what my standard deviation is. And report that, and it's going to output me a value. So if I say my mean is $10, and my standard deviation is $2, then at what point will 0.7, at what dollar value is 0.7, and it's probably going to be $12-ish. I don't want to do the math in my head, but about $12 would be your answer. So your output's going to be in dollars. And so if you're using norm.s.inverse, you wouldn't enter your mean or your standard deviation, and instead, if you said 0.7, it would say something like 1.1.
So we're giving the probability and we're looking for the z-value.
Yeah,
For
the z-value. For inverse, we're getting the z-value. For norm.s.inverse, we're getting the z-value, and for norm.inverse, we're getting the actual value.
It was $11, by the way. Pretty close.
Was it?
Yeah, it's
Close.
pretty good.
I was trying to think it through, but okay.
I just did that. Pretty good.
Thank you.
You're welcome. Okay, so normal distributions. Let's look here. So your next chapter you guys are covering is chapter 7. So if everyone turns to page 342 in your book. So number 15. It says a population has a mean of 200. So population mean is equal to 200.
Yes.
Yeah, 342. Standard deviation for the population, which is going to be a little squiggly guy. And our sample size is going to be equal to 100.
That's what it is.
One here. Let's open this up. We're saying that our population mean, our population standard deviation, and is what we're given.
Try making that bigger, please, like physically. Thank you.
So, our standard deviation for a sample is going to be equal to standard deviation of the population divided by the square root of our sample size. So, we'll get to that, why that's important in a second, but, so, that means, so a sample standard deviation is going to be equal to our population standard deviation divided by the square root of our sample size, which is 100, question on A is, what is the probability that the sample will be plus or minus 5 of the population mean? So plus or minus 5 of mean. So let's talk about what this actually all means. So we have a population and we're measuring, say, the cost of tickets to a concert. So the population mean for cost of tickets to a concert is $200. The standard deviation for the full population is $50. So we're saying that normally a ticket costs $50. Standard deviation is $50 either way. So if the ticket price is between $150 and $250, that's going to contain about 68% of our sample. And then most of our sample is going to be in between $100 and $300. So it's a relatively high-end ticket that we're talking about. So what we're doing is, for some reason, we want to test whether or not that population mean is true or not. So we're going to take a sample of 100 tickets purchased, and we're going to measure to see whether or not the mean price of 100 tickets purchased is equivalent to the population price of 200. And the reason why we're doing this is because, to go further on, what we'll start to do with these A/B tests is people will make claims on products all the time. So people will make claims on the life of products. In order to make a claim on the life of a product, we have to do proper testing statistically to make sure that life of the product claim is accurate or not. So what we'll usually do is we'll start with a population mean, or we'll start with a claim of some sort. And so we start with this claim, and then we try to say, can we disprove this claim? Can we say whether or not this claim is true or false, is not true? So if we can say the claim is not true, then we can say that we know for sure that your claim is inaccurate, you should change your claim. It's kind of what the basis of these next couple chapters is going to be. So.
So what did you do with the 5? Because I missed that.
Can you put it back on the
Yeah, so that's a sample standard deviation. So if we know our true population values for our mean and our standard deviation, which isn't super common, so we won't always know that. But for this chapter, we're always going to know our true population standard deviation values. Then the larger, if we take a sample, the sample standard deviation is going to be close to the population standard deviation, but the larger sample we take, so the sample standard deviation of the mean, let me correct myself there. So we're taking a mean estimate from a sample. The sample standard deviation of the mean is going to be dependent on how much variability there is in the general sample and how large of a sample how much variation there is in the population and how large of a sample we choose. So if we think about that, if we're talking about a population that has lots of variability, I'm trying to measure income of people I see walking down the street, and I only take a sample of 5 people, how close am I going to get to measuring the actual mean income of the American population? Not very close, because there's so much variability and my sample is so small. But if I end up calling 100,000 people on the phone and asking them what their income is, even though there's still lots of variation, my sample size has gotten larger, and so since my sample size has gotten larger, I now get a more accurate estimate of what I'm trying to guess. So if there's something with very, very little variation, I don't need as large of a sample, because the variation is so small, I'm more likely to get a true estimate of what the actual mean is. So for this example, we're saying that our sample standard deviation for the mean, if we're talking about this population, is 5. Now our question says, what is the probability the sample will be within plus or minus 5 of the population mean? So plus or minus 5 is what our actual standard deviation mean is. So we're saying if we're trying to estimate the mean, and the mean is 100 for the true population, and we end up one standard deviation above and one standard deviation, what's the probability we're gonna finish one standard deviation above and one standard deviation below the mean? 105, which is equivalent to 100 plus one standard deviation. And this is 95, which is equivalent to 100 minus one standard deviation.
Just because your N, your population's 100, that's why that's in the middle.
Yeah. So the mean, I meant 200, not 100. My bad. You're right.
Yeah, I was like,
200.
which one are we looking at, the sample?
I meant 200 there. 200. This is 195. So if my mean is 200, what's the probability that I fit between 1 and 2 standard deviation? I mean, one standard deviation above or below, which is nice because this ended up being a nice round number. So I can tell you from memory that one being within plus or minus one standard deviation is going to be 68%. That's not going to help you guys when you get to the test and you don't know what's going on. So let's think about how we're going to do this. So minus 5 and plus 5.
So is the minus 5 and plus 5 then the standard deviation and not the 50?
No, this is the question we're asking you.
Oh.
So we're saying, what's the probability that we get between plus or minus 5 of the actual mean that we're estimating?
The 68% is between 150 and 250, right?
No, for the sample standard deviation. So it's two different things. First is the distribution of the population as a whole. So between 150 and 250 for the whole population, that's going to be 68%.
Right.
But now if I go out for that whole population, I choose 100 people and I ask them what their average ticket price was, then there's going to be a 68% chance that my average ticket price is going to fall between 195 and 205.
Got it.
And so how we calculate that in Excel, norm.distribution. So this is still a normalized distribution, so we can still use norm.dist. What we're saying is we want to figure out the mean plus this value. So this mean plus this value is going to be our lower end of our probability. Our mean is 200, and our standard deviation is 5, because we're dealing with the sample standard deviation. We just do 1 for cumulative. And then we're going to do our upper tail, or upper point, 1 standard deviation above. It's going to be our mean plus the 5. So, 1 standard deviation, and again, what does our norm.dist give us? Our norm.dist gives us the area to the left of our point. So the first one, our lower tail, for 200 minus 5, or 195, 0.158 is this area here. So for our higher tail, which is 205, it's going to be this area all the way here. But what our answer is the area between 1 standard deviation above and 1 standard deviation below the mean. So, like we did last week, in order to figure that out, we take the difference of these two equations. Questions? Yep.
Can I see your equation for C9?
You're taking the mean of the whole population, but the standard deviation of the sample.
So the reason why we're doing the standard, so what we're saying is there's two ways to think about it. First, the first way that you guys learned last week is when we talk about a whole distribution of a population. Now, instead of talking about that, we're estimating the mean of a population. So since we're estimating it, we took a sample. So instead of using the population standard deviation, we're now using the sample standard deviation.
Is it possible to explain all the formulas? I think I got them reversed for some reason.
So
Thank you, Matt.
the first formula is we take the mean of the population, and we're trying to find, the overall goal of this question was, we're estimating this population mean. So what is the probability that we fall +5 or -5 in that range of 195 to 205? What's that probability? Given that the mean is 200, population standard deviation is 50, we took a sample of 100. So first, -5, this is the estimate for 195. So we're finding the area to the left of 195, or this brown area here is the first thing we're estimating. So in order to do that, we take the population mean, we add in this -5, and then we say that the population mean is 200, and our standard deviation, we're using the sample standard deviation right now instead of the population standard deviation, because we're estimating a sample. We're estimating the mean from a sample.
And the next one?
The next one is kind of the same idea, but instead of doing the lower bound, we're now doing the upper bound. So instead of 195, we're doing 205.
What happens if you use the other standard deviation? Population.
It's not going to be correct. But here's the thing. This type of question is they'll specify that. They'll say, hey, you know the population mean, and you know the population standard deviation. Now you're going to take a sample to estimate the population mean, and when you're given the population mean and the population standard deviation, you just calculate what your sample standard deviation is, and that's what the standard deviation you're going to use. And then later on in future chapters, we'll start estimating what the mean is without knowing the true population value for standard deviation. And then that's going to be a little bit different, and then we'll use something called a T distribution instead of a Z distribution. But this is, for now.
So is that sample standard deviation, is that a formula?
Yep.
Can I see that?
Yep.
So because it came out to 68.2% means that it was a good population, it was
The
a good
formula in the
sample?
book, it's over there.
What does that tell
For the
us?
So,
sample
so
size
first,
means.
the formula is just the population standard deviation divided by the square root of the sample size. So when we're dealing with this and we're estimating a population mean, then the larger our population is, the more accurate our mean estimate's going to be. So the larger this number is, the lower this number is, and the lower our distribution of possible outcomes is going to be. And then the larger the population standard deviation, or the more variances in population, the wider we're going to stretch out our possible range of getting an accurate estimate. And so what this is saying is, so +5, -5, depending on what the metric is. For this, 100 seems like a pretty decent population size to measure this, given the variation. And so,
Because you came up with 68% and it's 1 ± 1 standard deviation? I mean, is that?
Yeah, is that what the answer's telling you? Is
so
that-
the answer is telling you that
Can I get a
Probably,
calculation?
yeah.
What does it mean?
the correlation between the ±5 and the sample standard deviation actually being 5 is just kind of,
Random.
it's random. This is the
Okay.
book assigned it that way. So what we're doing is we're saying, we're trying, what this will help us do is this will help us say, if we want to get to a certain level of accuracy in guessing our means, then we have to get our population a certain size. So if I want my accuracy to be within 1 point, I want my mean, my actual accuracy of estimating this value to be within 1 point, and I already know my population values, then I know that 100 wasn't a big enough population to do that exact.
When you say 1
Question.
point, what do you mean? You wanna get it to 99?
I want whatever I'm estimating it, be it this being the price of a ticket, say I want to estimate the average price of a ticket, and I want to be within $1 above or below the true population value. Now, if that's my target, if I start targeting point accuracy, then I can say, what level do I want my samples to be? How large do I want my sample to be? This is what this can kind of help answer.
So can we just change your N to 200 and see the numbers change as a result?
Yep. And the main thing with this is we're going to start building these templates, and then the numbers are going to change. So our sample size went to 200. What are the odds that we're going to be with plus or minus 5? Well, now it's going to 84%.
Okay, I got it.
So the larger our sample is, the more accurate our samples become. But then also we've built a template here where we say, what if we change the value to, now we have a population where our mean is 7, and our population standard deviation is 1.25, and we take a sample of 30 observations. And now instead of this, we're going to talk about, we'll do 0.5 here. So, this is now a template where we can start plugging numbers into these formulas, and then it'll always pop out the values we want to see. So the key to this class for you guys is, one, being able to interpret what's going on, which is the harder part, but the easier part, what could be harder for some people who are like technically challenged, we can make that easier by making these these templates. So if you make these templates and you label them well, and you know what means what, this is the probability that our answer falls between these two values, then when these two values change, or when this value changes, or when that value changes, you can change these, and then your answer values will repopulate, and you're going to know your answer already. So next week, once we know for sure what's on the midterm, so I don't believe I have it yet.
So that percentage is your percentage chance of being right?
Being within those two.
Of being within the
the
bounds
bounds.
of the population mean and the population standard deviation. That your sample will be within the right
So
bounds.
this percentage here says there's a 97% chance that my estimate of the mean will be within a half point. Will be within one. Will be either a half point below or a half point above, whatever I'm estimating.
In this case,
These numbers change all the
Yep.
Would you be so kind and put the formula for the
Did he change all the
probability,
numbers?
the one that you were
Yeah,
just talking
that's
about,
fine. He changed the
B9?
numbers up top and changed the one.
Thank you. So it's the difference between those two.
It's the difference between your lower bound and your upper bound.
Got it, okay. Thank you.
So the negative 0.5 and the positive 0.5
Yeah.
in relation to this,
What do you mean?
in relationship to this data set is, it's not a percent, it's an actual, that's like
That's a
like
point
we're
value.
dealing in dollars.
Yeah. So if we're trying to estimate the cost of a sandwich, yeah, we're trying to estimate the average cost for a sandwich around these campus.
As
Then-
around $7, it's either $6.50 or $7.50.
Yeah. So if we were to say, I want to estimate, and this is before I know the true population mean, I'm just trying to estimate. I want to make sure that my estimate is between these two numbers. If these are my true population values, I would need to take this large of a sample. If I took a 30 sandwich sample, I would be 0.97. I would contain
90% of my 97%.
I'd have a
of my data would be
97%
within that.
likelihood that I'd be within 50 cents above or below the actual true mean value.
So Matt, are we gonna see the opposite when you have all those numbers, but you wanna find out how many observations you might need in your data set or not? Or is that going too far?
We could.
Go
I mean,
see.
in real life, that's something in this class you probably won't.
Okay.
In reality, that's something that people try to play with,
Yeah.
where we have different samples. I'm gonna send out a direct mail test, and I wanna see how people respond, and I wanna be 95% sure that something is better than something else before I send that out. Now I can start playing around with how large of a population do I need to test to before I can just roll out something as a winner, as a champion versus something else. See, that's something that happens. I'm not sure you guys would kind of get the logic to do that. I don't think you'll be asked to do it, but the logic is there.
Because there's still a lot more that goes into it. You need to know the population mean and this.
Well, you can have estimates though. You can have estimates of what you think these two numbers are, and then say, it's a little bit different than this, because this we're not testing the difference between two means, but we'll get to that later on in the class. So you're saying, I'm testing these two means, I know that these are the values I expect to be for the population. How large do I need my sample to be so I can measure a truly accurate statistical difference between two populations? So that's something that we'll kind of get to.
I'm really looking forward to that.
Oh, so much fun.
Alright, can you say again what the 97% is? I'm sorry. So what is the 97% then?
So
It's the
if
chance
if I'm taking a sample
that,
in order to estimate this population mean. So there's a population mean that we know, and I'm gonna calculate a sample mean. So it's gonna be different than my population mean, because the population mean is a true value, and I'm not gonna get to the true value, I'm gonna get to my sample's value.
Okay.
So if my population mean is 7 and the standard deviation is 1.25, then there's a 97% chance that my population mean will be between 6.5 and 7.5
for 30 samples.
for a population size of 30. Yeah. But if I only took a sample size of 3, now that's a very, very small sample. And even though this is relatively unvolatile metric we're looking at, the probability that I get within 50 cents above or below that mean value is now only 51%.
So what is the total population? It's just like infinity, or what, like if you're trying to take a sample, and you're saying, okay, I'm taking a sample of,
It could be, it
Something
depends how we
bigger.
classify it. So say if we're talking about the average price of a sandwich, it could be the average price of a sandwich
On
in
Tuesday.
all of Las Vegas, which for me to collect data, that's gonna be really, really hard for me to collect data to get every sandwich in Las Vegas for sale and get what the true price is. So a sample would be me randomly selecting different places and spot checking what their prices are.
okay.
So it's hard to get, the best way to think about this is it's hard to get population metrics on the US population. So we report what the median income is or what the average income is. We don't take a census that gets that information from everyone all the time. Every 10 years, we kind of take a census that gets most of that stuff, and even that isn't super accurate and doesn't really get everyone. So what we do as a country, in order to have these metrics which are important for public policy, is we do samples throughout the country where we take a sample of so many thousands of people and we ask them questions, and then based on their answers, we can assume what the population distribution is at that point in time. So that's why sampling is important. Or say that we run a factory and we produce light bulbs, and we want to advertise how long our light bulbs operate. So the only way to truly know that would be to take every light bulb we ever produce and then set them all on and just sit and wait to see how long they all last, and then take the average of how long they all last. When instead,
And never saw them.
we could take every 10th light bulb off the line when we produce 2,000 light bulbs, and then we have a sample now of 200 light bulbs. We can test how long those 200 light bulbs last, and if it's a relatively unvolatile population, then we can advertise what we expect the average life of a light bulb to be.
So are you trying to get to a certain percentage that you're comfortable with? Is there
Yep.
like a 97% or
Usually
90%?
for this class, 95% is what you guys are gonna get used to. So you want 95% confidence in things in order to state them as fact in an academic environment usually. But I mean, in the business world, we can get looser with those terms and declare things. But usually for this class, 90, 95, 99, but mostly 95. Okay. Let's try a different question. So page 343.
What question was that, by the way? Sorry.
That was
15.
15.
Chapter 7, 15.
Question 23. Economic Policy Institute periodically issues reports on wages of entry-level workers. Institute reported that entry-level wages for male college graduates was $21.68 an hour. For female college graduates were $18.80. Assume the standard deviation for males is $2.30. And the standard deviation for females is $2.05.
Try making that a little bigger, please, Matt.
Okay.
Thank you.
So question A states, what is the probability that a sample of 50 male graduates will provide a mean within 50 cents of the population mean? So, our sample is 50, which means our sample standard deviation
Average, right? The average is also the
Yeah.
sample standard deviation average?
of the mean, yes. Bless you.
Thank you.
So, that's gonna be equal to the standard deviation of our population divided by the square root of our sample size, which is 50 for this question. And then our low point, our high point. Our low point is our mean minus 50 cents, and our high point is equal to our mean plus 50 cents. So, if we have a sample of 50, what is the probability that we end up within 50%, 50 cents of the mean? We can go norm.distribution. This is our x value. This is our mean value. This is our standard deviation.
Are you doing just the males?
What was the?
Yep, just the males for question A.
Oh,
And then we want to find the area to the left of our high point. So, if we were to look at this as a distribution, here's our mean. Our mean for this value is $21.68.
Did you take the right standard deviation? Which one did you take?
I
the
took male.
male standard.
But did you take the sample deviation of the mean, or did you take the,
Oh.
no, the answer? Or, yeah.
Did I take the wrong one? Yeah, I might take the wrong one. So,
Can you just scroll over one of those?
Yeah, better.
okay. So, if our mean is 21.68, we're trying to find the probability that we fall between 21.18 and 22.18. Our low bound area gave us the area to the left of our low bound, and our high bound area gave us the area to the left of our high bound. So if we take the difference between those two, we find this area between them, and this area between them is a probability that we come between those two values.
I'm sorry, Matt, could you be so kind and explain that portion again?
Okay, so if we take the low bound, so when we use our norm.dis for 21.18, we get the area to the left of 21.18. But the goal is we want to find the area between these 2 points. So ultimately that's our answer. So we said, what's the probability that we fall 50 cents above the mean or 50 cents below the mean? So we want to find the area underneath the curve between those 2 points.
So only 6.2% falls below that.
Yeah, 21.8. So only 6.2% fall below that. So if 6.2% fall below it, and then our higher bound, 93.7% fall below that, that means our area is going to be pretty large. So instead of drawing it here, I probably should have drawn it out this way. But essentially what we're doing logically is, since we want to find the area between these 2 points, we can find the area to the left of the first point and to the left of the second point. And so the area between those 2 points is the difference between those two values. So the area to the left of the low point, high point, middling point, there's an 87.5% chance that, given
That sample size.
this sample size and these population metrics, that we'd end up 50 cents above or below the mean. So, questions on that?
So you want a higher sample size if you're trying to get to like 95%.
Yeah, if we want to be 95% accurate between those 2 points, we want a higher sample size.
Right.
So say then we say 50 didn't work, so what if we did 65? We're gonna get closer.
Right.
And what if we did 70?
Oops, hang on.
Oop, undo. If we did 70, that's probably gonna get us up 75.
Goal seek.
Yeah, you could do a macro on that if you want to.
You don't have to do a macro. It's built
Well,
in.
goal seek is a macro
Oh, yeah.
pre-built.
Oh.
So, question 2, or part B in this question says, what is the probability that a sample of 50 female graduates provide the sample mean within 50 cents of the population mean, $8.80? So, now we want to focus on the female population. So all of these formulas, instead of being on the male population, we can just drag them down to being on the female population.
You also have to change sample size.
Yeah, put the sample size back to 50.
Is that what the question said? 50?
Yep, 50. Yep,
And then you have to change your high-low formula too.
I did that.
It's still 50 cents?
50 cents, yep. So, if we're talking about a female population that's averaging $18.80 an hour, and the population standard deviation is $2 and a nickel, given a sample of 50, our sample standard deviation is going to be 0.29. So given that sample standard deviation, what's the odds that a female out of college makes less than $18.30? There's a 4% chance of that happening. what's the odds of the female out of college, or that we estimate the mean of our sample ends up being all females making $19.30? There's a 95% chance that our estimate is less than $19.30. So what's the probability that our estimate is between these 2 points? It's a 91.5% probability. So if we think about the male sample with the female sample, and 50 cents being that range that we're falling in, we have a higher probability of being within 50 cents above or below the female population. Why is that? That's because the female population is less volatile than the male population. And for this problem, the female population is actually a lower mean. So the relative value of 50 cents to the mean is lower. So the less volatile our population is, the more accurate we're going to be with our sample estimates. And the lower the value of our mean is, the more accurate point estimate-wise we can be.
So Matt, do we have like 2 samples of 50, one for female and one for male, or we have 50 as one sample and we have?
We had 2 samples of 50, one from females and one from males. So the first question was a sample of 50 males, and the second question was a sample of 50 females.
We could have just done the second.
Yeah, we could have
Okay.
just duplicated off to the same side. So C says, in which of the preceding 2 cases, part A or B, do we have a higher probability of a sample estimate within 50 cents? Females. Reasons why, mostly it's because of the variance is lower. There's lower variance relative to the mean, and the mean is lower in general. What is the probability that a sample of 120 female graduates will provide a sample mean more than 30 cents below the population mean? So, this is a little bit different. So now they're saying, what is the probability that a sample, we're still on females, but now we have a larger sample, and it says that the sample will provide a sample mean more than 30 cents below the mean. So now we're not talking about pinpointing it between a high and a low point. Now we're just focusing on one low point. So here, when our low point, when our plus or minus was 0.5 or 50 cents, we can change that to 30 cents. So what is the odds that a sample of 120 females is more than 30 cents below the population mean? The odds are 5.4%. So it's very unlikely. And the reason being, we increase our sample size and we also have a very low amount of variance within the population.
Is that a 1 minus that answer to get the question that you were looking for, or is that?
No, because what's the probability that you'll be more than 30 cents below, right? Mean more than 30 cents below the population mean. So that's area to the left.
Did you say very unlikely, correct?
Yeah, it's 5% about.
I think I probably missed the very first of this conversation.
So this is a different way to ask kind of a similar type of question. So the question was, if we take a sample of 120 females.
No, I got that. It's so the 30 cents below, we're actually talking about finding the sample mean.
Being more than 30 cents below the population mean.
mean.
Yep.
I missed that part.
Yep.
Okay. Thank you. Because otherwise, if you just wanted to find the probability that it was 30% below the population mean, you wouldn't go through any of the sample mean.
Yep.
exercise.
If it was just, what's the probability that someone makes a wage that's 30
in this
cents below.
population.
Yeah, then we just keep the population standard deviation there.
Okay.
This is a very particular question where we are sampling and trying to estimate the mean.
Sampling.
And that's
out
why
of
we
the
use this sample standard deviation.
Gotcha. Thank you.
You're welcome.
I don't know if I can either. What was
Questions?
the end of this question? So is it 0.5 or is it 1 minus that?
No, 0.5. So the question said,
I don't have the book with me, I
Sorry.
apologize.
so this question said, what is the probability that a sample of 120 female graduates will provide a sample mean more than 30 cents below the population mean? So we find that 30-cent point, and then more than 30 cents below is gonna be the area to the left of it. So since we calculated the area to the left already, we just go with that number. And the 5% makes sense, especially since we upped our sample size, which means our point estimate's gonna be more accurate. And the female population has a lower standard deviation. Okay, so questions on sampling to find the mean.
What question was that, what number?
23.
That was 23. Okay, that's fine. All right, so So another thing that we can sample for, if we're not sampling for the mean, is we can sample for a characteristic. And when we sample for a particular characteristic, we end up getting a proportion. So we want to say how many students are passing a course. So instead of saying what's the average grade of a student in the course, we just want to know how many students are passing a course. So now we have a proportion. So proportions are going to be so if we're concerned instead of about the average of a particular value instead of an outcome of a single event, we're going to have proportions, which are successes divided by trials. And if we want to find our sample standard deviation, and we're given our true population value, and we're giving our true population standard deviation, then our sample standard deviation is equal to
GMAT's coming back.
So, our sample standard deviation is going to be equal to the population proportion multiplied by 1 minus the population proportion divided by our sample size. So, let's do an example to help this make more sense to us.
Population proportion.
Okay, so the president, so page 348, question 31. The president of Dorman Distribution Incorporated believes that 30% is our proportion. Believes that 30% of firms' orders come from the first-time customers. A random sample of 100 orders will be used to estimate the proportion of first-time customers. So, this company is not interested in, they have a particular question they're trying to solve. They want to see how many first-time customers they have. So they're not interested in so much of what the values are or estimating the mean value of an order. Instead, they want to estimate how many of their customers are truly first-time customers. So in this case, a success it's not a success in the way we think of it, but statistically a success is yes, you are a first-time customer. That makes you a success. And our number of trials is a total number of customers that they have. So they're going to take a sample of 100 customers. So, assume that the assumption of the president is correct, and that the true population proportion is 0.3. What is the sampling distribution of P? Let's get that one. So first, let's find our standard deviation. So standard deviation of P is going to be equal to the square root of our population proportion times 1 minus population proportion divided by the size of our sample. So, this equation written out in Excel is going to look like this. And so you're going to want to be careful to make sure that you have your parentheses around everything you want to have your parentheses around. And the best way to do this is to make sure you get it right one time and then kind of keep this format, like I said, and then copy this format over to a new sheet when you do a new question. And start using these similar formats to solve all of your questions going forward. So, standard deviation of our population, our proportion is 0.45, 0.045.
Is that the answer to A?
Pretty much. What is the sampling
Pretty much.
distribution?
Kind of, sort of.
So sampling distribution is the standard deviation of the
What is the sampling distribution? What is P with the line over it?
population, or the probability. So P with the line over it, is that probability or?
That's your proportion. So P
Yeah,
with the line
proportion,
over it,
sorry.
P without the line over it is your population proportion. P with the line over it is your sample proportion. And that's gonna be the same with X when we do means. If we have mu or X without the line over it, what?
He's just grunting.
If you have X without the line over it, that's a population mean. And if you have an X with the line over it, that's a sample mean.
So then that's
So
the
this is
answer.
proportion and sample proportion. What is the sample distribution
The answers to the answers.
of the sample proportion? The sampling distribution of the sample
Answers needs to
distribution.
be off.
Right over my head.
understand what it's asking. Portion. Okay, what is the sampling distribution?
And the sampling distribution is really just, we can draw it out. Our mean is gonna be 0.3, our standard deviation is gonna be 0.045, which means 68% of our population is gonna fall between 34.5% and 25.5%. And then almost all of our population is gonna fall between 21% and 39%.
What?
So.
You just add it, so you just added 0.3 plus the 0.04?
Yeah. Yep. That's
Yeah,
it.
okay.
Yeah, I'm just saying that the distribution of our sample is gonna be that way. That when we talk about a full distribution, we're talking about kind of drawing that bell curve and then illustrating what our mean is and our standard deviations away from our mean, what they look like from a value perspective.
Would you mind to illustrate? I'm kind of like a visual person, so if it's possible, maybe.
Yeah, so thanks, Jeff. So our population proportion is 3, which is gonna be our sample. We assume that if that's our true population proportion, our sample proportion we'd hope would be based around that. 1 standard deviation above, 1 standard deviation below. This is gonna contain about 68% of our population, is going to be 0.345 and 0.255. And then 2 standard deviations above and 2 standard deviations below is gonna be 0.39 and 0.21. So the whole realistic realm of possibilities for our mean estimate of the proportion is going to be between 21 and 39. So we know that our first time customers is going, in our sample, with some pretty good confidence, we know that it's gonna fall somewhere in this range of 21 and 39%. And that's basically all realistic outcomes. Now, if we wanna narrow that down to say, what's 1 standard deviation above and below, that's where 68% of our possibilities are going to be. We're gonna be between 0.255 and 0.345. So, this is our distribution of what our sample proportion should look like, theoretically. So B says, what is the probability that the sample proportion will be between 0.2 and 0.4? So we have a low, we have a high end. A low end is 0.2 or 10% below the mean, and our high end is 0.3 or 10% above the mean. But when we drew out our distribution, and we said 2 standard deviations above or 2 standard deviations below, we're going to contain about 95, 96% of all possible outcomes are going to be in between those two. We came up with 0.21 and 0.39. So if we're saying what's the probability we fall between 0.2 and 0.4,
99%.
it's going to be close to 99, 98, 97. It's going to be really high up there. So to figure that out, we use our norm dot distribution again. Our x is the 0.2, our mean is the 0.3, our standard deviation is our standard deviation of the proportion. So, again, we do it for both. Our second x is 0.4, our mean is 0.3, our standard deviation of proportion is 0.045. So what's the probability that we fall between these two? We take the difference between the two? There's a 97% chance that this sample has a proportion of first-time customers between 20 and 40%. But we kind of knew that as soon as we drew our sample distribution, because we knew between two standard deviations above and below, we had 21 and 39. So the second part of the question says, what is the probability that the sample will be between 0.25 and 0.35? So now we want to get slightly, we want to say, what if we, instead of had a whole 10% above and below the mean, what if we only went 5%? We can just change those two values.
Why do you keep saying percent above and below? You keep saying 5%.
Percentage points above and below.
Oh.
Because this proportion is a percentage.
Oh, sorry, gotcha.
So we're saying.
I'm still thinking in money.
Yeah. So proportions, though, we're going to think always in percentages for proportions.
Okay.
So we're saying if we're 5, instead of being 10% above and 10% below, we're now 5% above and 5%
It's
below.
confusing because.
Percentage points and not percent of the
Probability.
Yeah, yeah. So we end up here at there's a 72% chance, which is pretty close to 68, and at 68 we said we'd be between 0.255 and 0.345. So they're a little bit different, but they're pretty close. So our sampling distribution kind of gave us these answers before we calculated them, which helped us know they're correct.
On the formula, please, for the longest.
Which one? Longest?
Yeah.
So your x is going to be whatever you're estimating to be at the low point or the high point. And then your mean is going to be your population proportion. And then your standard deviation is your standard deviation of the proportion. And then you just always put 1 for true, 1 or true. It's up to you.
So Matt, the proportion is always going to be given to us, or do we need to, in other, like as we go a little bit more into it, we would need to determine or find out the proportion?
So
I could give
For
you
now-
some trials.
yeah, so for now,
I'm kind of-
it's either one of two things. It's either going to be given to you and you're going to be given these numbers, you have to figure it out, or you could be given a population. You could be getting a set of data. He could give you 200 data points with a yes/no answer, and then you have to calculate how many yeses there are, and then that's going to give your sample proportion. But your population proportion is always going to be given to you because
Population.
But the
it's your
number-
population.
The number of observations are all that proportion, it's not the bigger sample, correct? And
No, the number of observations is a sample.
so the proportion.
So the proportion is all the customers that this company sells to.
Okay.
That's the population. So the population proportion is 30%. So instead of looking at all of the customers they sell to, we're just looking at a sample of 100 of those customers. And so this can come from, maybe we're not collecting data on something, but we have a concept that we think our business runs and operates, and we get a certain idea that we all kind of operate on that we think exists, but we don't collect data on. So now, this company thinks that 30% of their customers are new customers. So now, instead of thinking that, this company's trying to prove that out. Questions on sampling distributions of proportions? You guys look in your, let me see, there should be a, or I guess there's not yet. That is, basically that's all of chapter 7. Questions on chapter 7? Basically, we started out looking at means, measures of central tendency. So we started talking about our mode, our median, our mean, our standard deviations, our min, our max, our ranges. So then we started talking about applying a distribution of values and normalizing it and then standardizing it, and that's what we did in homework 2. And so now we're talking about estimating a mean. So all of this stuff is pretty, it's difficult in the way that we're talking about things that have similar words that describe different concepts. When instead of talking about a distribution, now we're talking about the distribution of a mean estimate. But we'll build from this to starting to test the differences between multiple samples and seeing if a sample disproves, if a population changes over time and one sample disproves another sample, and stuff like that. But I don't think we want to get into hypothesis testing tonight because that's a big, long, drawn out thing. But do we have any questions about this?
Thank you, Matt. Appreciate it. See ya. Have a good night.
Do you know when your midterm is due Wednesday?
November 1st.
November 1st, so it's not.
Wednesday
The day
before the
after
next
we meet.
class.
So you'll have class
We'll have
on
2 Tuesdays.
this
before that.
week.
Friday and Saturday.
So we will have Tuesday, the 24th, and then we'll be here on Halloween.
Yep.
Isn't that exciting?
Not me.
So we'll have, here's what's gonna happen with that. You guys are gonna get your test on Friday, it looks like.
Yeah.
We're gonna go question by question on your test. We're not gonna answer the questions he gives you. We're gonna answer an exact replica question.
Okay.
And so we're gonna work through the understanding of how that question works, and we're gonna build a template that then we can then use to answer the question on the test.
We're gonna do that on the 24th or the 31st?
The 24th.
Okay.
So we'll have that all that ready on the 24th. If everyone is freaking out, then we can then discuss whether we wanna do 2 days on the next week. But the 24th and then Halloween, we'll have questions just for all your midterm stuff.
Thank you, Matt.
And then you'll probably get homeworks too, I imagine?
Yeah,
I
we
have
want
to
to
go
be
scare
more.
kids on Halloween. Every year.
Yeah, could we consider rescheduling?
We could consider, I'm fine with moving Halloween to a different day. It's up to you guys.
Can't move Halloween.
My kids will appreciate
We
that.
can move our study
Yeah, we can
session.
move study sessions. We can move the study session. We can plan to have 2 study sessions that week if we feel so obliged. I don't know what time your homework is, your test is due. It looks like midnight. So, I mean, I won't be with you guys at midnight. I'll be sleeping. So we can definitely do a study session on the 1st. If that,
That's the other cohort's study night, right?
well, it was supposed to be tonight, they're not here, right?
They're
So-
done almost. I could check.
I think they don't, I think they stopped studying a long time ago.
Yeah, I'm down with that one. 'cause-
I know them. I could probably convince them to move to a smaller room.
Yeah, that's not fair.
Okay, so I'm gonna communicate with the rest of the people that were not here today, so what are the dates that we're meeting then?
Is it
We're doing the 24th again. We're doing Tuesday. We'll talk about it on Saturday.
Okay.
But let's just plan right now that we'll do the 24th,
24th,
we'll do the 31st,
31st?
and the 1st. And then if we all get together on Saturday and everyone's like, I'm not gonna be here on the 31st, and then we'll just do the 1st.
You think you can get through everything on the 24th?
I think we can get through a lot of it, pretty much all of it.
For kids, it is.
If not, we can also do the 25th too. So, we can see how that goes.
Okay.
That'd probably be better than Halloween.
But what I'll do is, depending on these 4 chapters, I'll send you guys out a study guide after this weekend. Similar, the one I gave you, there's nothing to really study guide for your first 2 days of class, because all of that is just pretty simple homework. So we'll have a study guide that meets chapters 7 and 9, and I'll send that out, so you'll get that probably Sunday-ish. And then you can start working through your homeworks, your quiz, your midterm yourself. And then 24th, we'll work through all the questions similar to your midterm. And then the 31st/1st, we can answer midterm questions. But ideally, we'll be done with the midterm at that point, so it's just a quick midterm questions, and then we finish up homework 3.
That was on the 1st or the 31st?
Both.
Oh, really?
Both for now.
So they'll be the same, essentially, it'll just be for two groups of people?
Yeah,
Okay.
unless everyone's not gonna be on Halloween, and then it'll just be one group of people on the first. But I'm willing to do both.
I will gladly be here on Halloween.
So will I.
Yeah.
I don't know, I'm not much a Halloween guy, mostly because I'm grown me.
Without kids.
I know kids. I bought candy for kids last year, and no kids came. It was real depressing.
Kind of a big deal for the kids. At least my kids.
Yeah, big
We'll go
deal.
from
Isn't it trick or treat like,
You don't like it?
don't most people do it on Friday or Saturday? The night of.
What about the razor blades and the candy, guys? That's what I should
All
worry
year.
about.
Well, we got about 4 rounds of it. One at the school, one at the church.
So just double
And the
checking
real
that it
night.
would be
And
6:30
the-
each of these.
Yep, 6:30. 6:30 is our start time now.
Trunk or treat. Trunk or treat. Yep, got that.
Really?
I'm out of here. Now I get to
That's
go.
good. We usually.